Good afternoon, everyone. Thank you for joining us today. My name is Marissa Waterman. I'm the Marketing Director here at AAEES. Here with us today, we have Professor Vladimir Novotny. He was a professor at Northeastern University in Boston and Marquette University in Milwaukee. Today, Professor Novotny will be discussing decarbonization of integrated urban water, energy, and solids management. Before we get started, I just want to mention that you'll be able to message your questions at the end of the presentation. And once the presentation's over, you'll be able to type your question into the attendee chat panel you see on the left-hand side of your screen. I'll also put the email address of Dr. Novotny in the attendee chat so you can email him directly with any questions you might have. Okay, let's get started. Good afternoon, Professor Novotny. I hope I pronounced your name right. Thank you for joining us today, and we're ready when you are.
Okay, I'm ready. So good day, everyone. Thank you for connecting to this webinar on a very important topic, which would be decarbonization of the integrated water, energy, and solids management for urban areas. This term of decarbonization is kind of very important today because even Bill Gates is very interested on that. I thank Ms. Waterman for introducing me and the American Academy of Environmental Engineers and Scientists for organizing that. I have to get my slides on. I don't see my slides. Okay, here we go. Okay, so that's the introduction. This is how I used to look. In the webinar, we will start with something to outline about both global warming problem, greenhouse gases, energy sources, current use, water and solids management systems, near future more sustainable biogas systems and technologies, are introducing hydrogen because that's probably what will save maybe the world from this dilemma we have with global warming. And we compare the alternatives. I briefly say something about negative emissions and conclusion. Okay, the problems caused by global greenhouse gas emissions are basically, you know, that it's global warming, droughts, flooding, hurricanes, sea level rise, ice sheets and glacier melting, methane emissions from tundra, plastic pollution, harmful algal bloom, forest fires, loss of coral reefs, and I can go and on because this is becoming already a very serious problem. The sources of this excessive greenhouse pollution, emissions are basically everybody. Again, you know that it's but it's on a large scale. It's now burning fossil fuel, again coal, petroleum, gasoline, etc. Fossil energy used by industries in steel, plastic, aluminum, others. Production of industrial fertilizers, making hydrogen even from natural gas and cement, emission of methane from natural gas extraction and from agriculture, emission of methane from anaerobic decomposition in landfills, sludge digestion, car emissions, forest and tundra fires caused by humans and lightnings, methane emissions from tundra on large scale, tundra permafrost, and which is caused by global warming. This chart has been published quite often, and shows carbon dioxide concentration in the atmosphere in Hawaii on the large Mauna Kea Hawaii mountain, which is about 4,200 meters high above the sea level, much higher. The largest, actually, the largest mountain if you count from the bottom of the ocean. So it's far from anywhere, and so the reflects actually the global warming of worldwide. So you can see the steep increase of the CO2 and methane. Methane is as bad as CO2 as far as the global warming potential. The in the pre-industrial age, the concentration of the CO2 were about around 280. Now, as you can see, it's exceeding the 400 and 400. And if it increases, if this is doubled of the pre-industrial age, the temperature in the atmosphere will increase at least maybe 1.5 to 4 degrees Celsius. Methane has, by the way, the global warming potential 25, and carbon dioxide global warming potential 1. So everything is related to CO2. The CO2 equivalent now will be, once it's in the atmosphere, it will stay there for a long time. Now, in 1997, in 192 countries established a Kyoto Protocol. The Kyoto Protocol basically said that the near goal is to decrease the atmospheric emissions by at least 5% by now or before, and limit global atmospheric warming to at least to 1.5 degrees Celsius over the pre-industrial levels by middle of the century. So this is the goal. But if business as usual, if we do as we do right now, or maybe slightly better, these 1.5 degrees will be reached by in about 10 years. So we don't have much time. And now, so the International Panel on Climatic Change, IPCC, met again in this year and gave the warning to the human population, to people, about they call it code red. That the warning is that if the society doesn't act, the situation will be far worse, and there is no doubt that these emissions were caused by the humans. And Earth is actually reaching very quickly a threshold from which there will be no return unless you start removing CO2 from the atmosphere. So the decarbonization of the economic sectors is needed to avoid the hot house Earth status. If, as I'm saying, we might be already very close to that hot Earth status. Oh, excuse me, that should be. So what is the basically net zero? We try to reach the net zero carbon emissions, and what is the decarbonization? So net zero emissions mean that if you they're achieved, that any CO2 or any GHG greenhouse gas emitted by a utility or by a city is offset by equivalent amount of CO2 removal and sequestration from the emissions. Decarbonization basically means removal of CO2 equivalent emissions from sources of the greenhouse gas. Full or deep decarbonization means that no GHG emissions and should be we should have no CNG emissions and start beginning to remove the CO2 from the atmosphere, which is called negative emissions. And Professor Sachs from Columbia University basically is an expert on this global decarbonization, says that climate decarbonization stabilization requires full decarbonization of our energy systems and net zero greenhouse emissions. Decarbonization is the only safe haven from disastrous climatic changes. It's the ultimate goal. Here is a picture again of the total situation. The left rectangle is the sources of energy. The sources are petroleum, natural gas, renewable energy, coal, and nuclear power. In the middle is the production of the electricity. As you can see, that's they didn't print the right. Okay, excuse me for that. There should be animation. Basically, what the black rectangle is the losses of the energy when we produce electricity. 65% of the energy in production of electricity is basically lost in heat and carbon dioxide. 35% is converted to electricity for residential and other uses. Now, this forensic is missing animation was should show that the cross means that this source of petroleum should be eliminated. Also, coal should be eliminated because this is a fossil source which is difficult to control. I was thinking about natural gas. What to do with natural gas? This is also a fossil source of energy. But now we have something which is called blue hydrogen. Natural gas can be relatively easily converted to hydrogen and carbon dioxide. In other words, you have a CH4, so take out the C, and you have two H's. So that's easy. So, and hydrogen is the goal probably for the future. It's the goal of future. Now, again, I also was thinking that our people are thinking that petroleum or oil should be also decarbonized. So, but the chemical industry and plastic needs that. So, if there is a control of the CO2 by carbon capture and sequestration (CCA), that probably will continue in the future. Now, this chart is in quadrillions of British thermal units, but so it had to be translated into terawatts. And if you like numbers which have 15 zeros, this is it. So total energy production is about 29 terawatts hours per year for energy use to produce energy is electric energy. Only 10 terawatts is used, and again I cannot read it, but again per capita electric energy roughly is about 29 kilowatt hours per day per person. So what I'm in conclusion to this slide, we have to solve the problem of CO2 emissions from the petroleum, get more or less rid of the coal mining. I've got some personal reason for that, and start making renewable energies and keep some nuclear energy. I put it into a table. This table, which shows that what should be the energy production in every 10 years. Now on the right side here, this is the official forecast of the Department of Energy. And as you can see, the Department of Energy in February of this year still has a lot of coal being used for energy, and dramatic increase of the natural gas. Now, this probably would not solve the problem. This might even make the problem worse. Nuclear energy probably will stay more or less the same, but more or less the same. But there is some decrease because there will probably some of these power plants will be decommissioned. Hydrogen, air, and geothermal energy must be increasing. Now here I have in these two arrows that anticipated conversion of the nuclear energy, nuclear gas, not nuclear, natural gas into the hydrogen. So that means that the hydrogen will be increasing. Hydrogen is the energy source of the future. Here I would have the calculation is what is the emission of carbon dioxide per kilowatt hours produced in power plants. So it started about 0.6 kilogram. The data for that basically say that coal production energy from coal is about 1 kilogram of CO2 per kilowatt hour. Switching to natural gas will bring it down to about 0.6 kilogram per kilowatt hours. Now, all the other sources are basically nuclear, wind, geothermal, hydro obviously have zero CO2, so this would be the goal. Now, for comparison, France still had over 10 years ago has 0.1 kilograms of CO2 per kilowatt hour, but that's because they heavily rely on nuclear energy and hydropower. Similarly, Austria, Brazil, Italy, Norway, Paraguay, Switzerland, this where hydropower is dominating. We have also problems with solid waste. The solid waste in 2015, the US generated about 238 million tons of municipal soil waste. 35% was recycled, 30 was combusted with small energy recovery, and 52% was discarded into landfills. Landfills are sources of methane, very serious sources of methane, and methane, as I mentioned, is at about 25 times more potent gas than carbon dioxide. Now, until about 2017, most of the recycles went to China, which maybe to some other countries like Vietnam, Indonesia, and which they use it as a raw materials. Now in 2018, China said, "Stop! We don't want your garbage." So now what's this? I don't think it has improved much. Today, most of the garbage, let's say, is put in landfills, even with recyclables. So this is a situation which is not which is not acceptable. Now there is kind of push to go away from the landfills. Actually, but this is one of the goals, to have a net zero landfills use in the future, which is possible, but not fully. Now, European community is not stops funding of the landfills after 2030. So we'll see. Now, in solve the problem of this integrated water, energy, and solids management, we can do it in a integrated, I would call it vertically integrated water, energy, and solids. But the solutions are in a distributed system, which is, let's call it horizontally. So in buildings, you can have water conservation, heat and cooling, energy recovery, zero-scape landscape, roof solar panels, conservation, passive energy, green roofs. On district, what we think about district management is basically black and gray water separation, stormwater capture, drainage and storage, providing ecological flow to the urban stream. And regional may be integrated where all this energy recovery, or most of the energy recovery, can take place. It also will be the water can be used for recharging the groundwater, and so that probably in this new situation we will need new solid waste recycling facilities and processing of solid waste. Water use in the United States is very high. As you can see, this is in liters per capita per day. They might have some international participation in this workshop. So the US is very high. It's because of the use of water for irrigation of the lawn. I was saying that why people grow lawn if they don't have an animal which would eat the grass. But anyway, so the highest water use is in states which are used to be desert and do not have water. So water very often they have to be brought from distance. Now, the studies have been made how much water use can be reduced by water conservation, maybe different landscaping, the landscape water use, and this study was done by American Water Works Association. It's like 2 decades ago, but it's still kind of valid. Would bring the U.S. Water use to about European level, which is around about, let's say, 120, 150 liters per capita per day. Now, obviously, third world countries have very, very low use, maybe less than 50 liters, but that's about already the minimum. 50 liters is the minimum water use, so it's like extreme saving. So we have to, but bringing water needs energy. So there is the fossil energy used to bring water. Now, this is now if you look at the domestic energy, so here's the circle. Now here here I'm emphasizing the water heating. Use of energy for water heating is very large. It's about 4.5 kilowatt hours per capita per day for heating. We have also space heating, which can be controlled by, let's say, insulation insulation and roof, green roofs, etc. So there are a number of upper devices which can be used for reducing water use, for water savings, flush toilets, flushing the toilets. We have also passive energy, which can use the which can reduce the energy. You can put solar panels on the roof. We can large houses can collect the storm water and store it and reuse it for toilet flushing, etc. So there's number of things which can be done to save energy in a house. Another way to save energy is using heat pumps. Heat pumps can use on-site source of energy. Again, heat pumps can take energy from air to air, water to air. Air means that this is take cooling from the outside air to cool the inside, water to air, water to water, ground to air, and water. Now, air to air, water heat pumps air to air heat pumps are very common, but they have some problem with not very efficient use when the temperature gets very low. Let's say below 5 degrees Fahrenheit or below 10 degrees Celsius. But if you have a ground to air, then basically the use of a heat pump is unlimited. You can, because if you put the pipes of the below the freezing depths, you can actually get a lot of the energy. Heat pumps are very efficient. You need about 20% of energy from the grid to get energy you need to heat water and air in the house. Now, this is an example of the house, the house level that is almost perfect. This house is a Bullitt Center in Seattle, and this has practices which already has negative, which is better than net zero carbon emissions, and no water waste in the building. These practices include energy conservation, geothermal energy, as I just mentioned with the heat pump, roof solar panels, rainwater harvesting, waterless toilets, black water and solids, aerobically composted, etc., etc. This is example. This is not to say that every house 40 years from now will be like that, but it just says prove that it can be done. It can be done that you could have a better than net zero. In other words, this house produce more energy that it uses. Well, let's say what we can get other energy, what we can again do with energy and other resources from used water and wastewater solids. So the current systems are of we rely on aerobic used water treatment and anaerobic co-digestion of sludge with biodegradable municipal solids. That's the top of the current technology. Aerobic treatment uses energy and emits CO2. Co-digestion of sludge with biodegradable waste solids and liquids produces more biogas but also it produces residual solids. Typical biodegradable solid food and yard waste production in the United States is about 0.5 kilograms or something over a pound per capita per day that can be co-digested with the sludge from the sludge from the wastewater or used water treatment. You can add sometimes some city also in suburban manure. Airport de-icing fluids can be added and co-digested with biodegradable waste solids. And electric energy can be recovered also from biogas by turbines and generators. This is an example of the sludge digestions in Singapore. So Singapore is about 5 million people, so you can see how big it is. Now, if you look at the aerobic treatment with classic, so it uses about 1 kilogram of 1 kilowatt per hour per kilogram of influent COD. It emits about 30% of the COD. 30% of the COD, chemical oxygen demand, is emitted as a carbon dioxide. But anaerobic digestion or co-digestion can make about 0.25 cubic meters per kilogram of COD, or cubic meters of the biogas. And so here we can make, and 35% of the COD goes into digested, which this is the output from the digested tanks. Let's go to the next slide and see what treatment this is used at the beginning of the 20th century. Is aerobic biological treatment. Biological treatment for used water, treating treating or mixed sewage and separated black water. If you separate gray water from the black water, it can be aerobic membrane, completely mixed tank with membranes. Trickling filters can be used because of the trickling filters that use very little energy. This is so-called Barden Pope to Barden for treatment plant to give a credit to my friend George Barnhart, James Barnhart. This is a anoxic and oxic double reactor, which recirculates nitrates to eliminate nitrogen from the influent. I don't know much about the separate sequenced batch reactors, but what it means that basically you fill the wastewater reactor with the wastewater, aerate it, they make it decant and clean the settle and take the clean water out. But the thing about this type of treatment is that between 50% to 70% of incoming COD is converted to CO2 and bicarbonates. And the system uses a lot of significant amount of energy. So current aerobic used water treatment and anaerobic co-digestion sludge with those biodegradable municipal solids. As I showed, the aerobic treatment basins reactors emit the CO2. Sludge goes into the co-digestion. The energy is used, and emission of CO2 we can have energy of CO2, and no, we have some CO2 emissions. We can co-digest the sludge. Typical biodegradable solids and wastewater production is about 0.5 kilograms per capita per day. That can be co-digested with sludge and produce biogas. Electric energy can be recovered from biogas by turbines, and now, but if we look at it, if we just take the used water or wastewater only, there is not enough energy in used water. Energy potential, let's say that we start with about what the Europeans call person equivalent, PE. Person equivalent is about 130 grams of COD per person. This 130 grams of COD per person let's say, assuming some removal is reduced to about 123 grams per COD. Use digestion, you can produce about roughly 0.51 kilowatt hours from that. Total energy potential would be about 182 kilowatt hours per year. 35% efficiency energy production is about 64 kilowatt hours per year. Total average energy use related to municipal water use is about 365 kilowatt hours per capita per year. So in order to be net zero, we have to include other sources and convert the water treatment plant to integrated resources recovery facility. Okay. So the first thing which comes to mind is to integrate municipal solid waste. The majority, obviously, of municipal solid waste is deposited into landfill, where it slowly degrades, and the decomposition emits about landfill gas, which is mostly methane and CO2. Landfill gas capture needs capping of the landfill. About 60 to 80% of this landfill gas can be captured and added to the biogas that will be used for production of electricity. There's a leachate. Leachate is a fluid that is created by landfill. It's highly polluted. Maybe the COD would be 20,000 plus. So that can be added to the digestion and make a biogas, or it can be the captured landfill gas can be made into electricity right next to the landfill. This is a picture of the landfill power plant in Wisconsin. It produces electricity and adds it to the power grid. Now, with solid waste, again, we have the solid waste can be co-digested, it can be incinerated or gasified, and it can be recycled. Now, in the total production of municipal soil waste, which can be reused, is about 2 kilograms per capita per day. Kilograms per capita. Well, I would like to point out the plastic. the plastics are made from fossil petroleum. So in other words, if you would digest plastics, it basically this emission has to be counted as a fossil emission. So this is again some of it recycled. So we have to recycle, maximize the recycling. Here I can kind of put make a chart of oh, excuse me. Oh Jesus, I just got out. I'm sorry. I need help.
What do you need?
I clicked something on my mouse out.
Okay, what slide do you want to be on? Do you know?
I'm on slide about, I don't know.
You're on slide 24.
Okay.
Do you know which slide? I'm sorry?
I don't see anything now.
You don't see any slides?
No.
Okay. Well, the slides are still on, so I'm not sure. I'm not sure what you see to get it back. We can take a pause, we can take a break, and you can see if you can get it back.
I'm kind of I cannot. Okay. Okay, I'm back. Sorry.
Okay, great. That's okay. Go ahead.
I'm trying to get my picture out. That's what I'm saying.
You can just click on the camera icon if you want to turn your webcam off, but you don't have to.
Okay. Okay. Here's a current advanced, I would call it advanced 3 lines of the integrated resource recovery system with the traditional process linked to urban metabolism. So urban metabolism basically is water, energy, food, chemicals, materials, are there transformed, metabolized to used water and municipal solid waste, which can be recyclable. So this system has 3 lines. The first line is for used water, which is the aerobic treatment, biological reactors, primary clarifier, membranes, and you could produce effluent. There is a CO2 is produced and emitted from the biological reactor. The sludge goes to digester, but it can be called biodegradable municipal waste can also be co-digested. So you need some solids preparation. Some people put hydrolyzer in front to basically hydrolyzer like cooking the waste to get more methane out of it. The product is biogas, methane and carbon dioxide. The line 3 is basically the line from the biogas which comes from the landfill. The landfill is capped. So basically, you produce the biogas. From biogas, it's combusted, it goes to the turbine. Some heat from the turbine can be recovered by boiler and provide steam for the hydrolyzer. So if we look at the if you look at the balance, the assessment of which I put it like in a table. So we have three lines: water delivery and treatment. We have digester. We have landfill, power plant, or we have water heating. I kind of when should have identified energy used for water heating, which is very high. Actually, it's very high. It's the highest energy used, and also highest fossil fuel use for warming water. Now we have greenhouse emissions. We have other emission of CO2, and then we have a CO2 credit for producing energy. Now this system, I'm not going to go through every number. So again, the system is highly positive, so which means that very high positivity of the CO2 emission. I will show that in the graphical form at the end of my presentation. So this system is not net zero, and it's not even it's a big difference between the energy use, which is about 5 kilowatt per capita per day, and 3 kilograms of CO2 emissions added, so about 3.6 kilogram, versus the credit, which is about 1/10 of it. So this is not a sustainable solution to the problem we have with CO2 emissions. Now, incineration. You think that by incinerating garbage, you're creating an energy. Actually, people use that waste to energy title for this type of practice. So again, it starts with taking the combustible waste. It's burned. It's burning produces some steam, which can go to turbine and generator. But there is a lot of devices which have to clean the air, because this the emissions of basically are fly ash, sulfur, nitric oxides, toxic metals, dioxins. They have to be removed from the flue gas. So in order for flue gas to be eligible for emissions into the atmosphere. Now, what happens then? Instead of let's say several kilowatt hours, you can make per capita per day. You can make it's just barely you break even. Energy yield from incineration is less than 1 kilogram. Like 1 kilowatt hour from 1 kilogram, and sometimes if the feed is moist, you have to use natural gas, so you don't actually make any energy. That's why EU is in process of cutting out the funding for new incinerators. So if you kind of summarize, sustainability outlook and problems with current water and municipal solid waste systems. The traditional aerobic water reclamation system uses more energy than contained in the organics in used water and sludge. The energy needed to treat, transfer, and deliver water to the city user is significant. It's about 1 kilowatt hour per cubic meter of water to maybe 5 kilograms, maybe even more per cubic meter. Household water heating requires far more energy, about 10 kilowatt hours per cubic meter of water. Roughly 50 liters, so about 1/20th of is used per capita per day. So you divide it by those 10 kilowatt hours by 20, but it's still a lot. Part of that heat energy could be recovered in the future or even now by heat pumps. Combusting digester gas for producing electric energy emits carbon dioxide. So without expensive energy demanding air pollution control, incineration of municipal solid waste emits toxins and fossil CO2 from plastic. So the solutions scientists are suggesting is use anaerobic treatment. Anaerobic treatment is basically 4 steps decomposition of organics into methane and carbon dioxide. But if you stop at the third step, which is called fermentation, the third step, the products is also hydrogen and carbon dioxide. So if your goal is to produce hydrogen, then you would stop at the third step of anaerobic treatment. Now, anaerobic treatment can produce 3 times more biogas than aerobic co-digestion. So this is again maybe a step forward to focus maybe on the fermentation only. People have tried it, but it didn't work. It's not working just on standing up alone, because there is still a lot of the COD would be still would be unused. Fermentation and methanogenesis. Product of low pH fermentation and oxidation are acetates, hydrogen that are used by methanogen to make methanes and methanogenesis step. So, but anaerobic treatment can be used, and it could be made very efficient. The anaerobic sludge blanket reactor, which is the most common unit, can have about the same COD removal as classic aerobic treatment. Professor McCarthy from Stanford University with his team led by Professor Kim in South Korea made tests that, for example, two-step anaerobic treatment would produce very clean effluent that could be acceptable, very comparable to aerobic treatment. And it will also produce a biogas that can be converted to energy. And so this is an intermediate solution. Membrane filtration microfiltration is a very useful, and then you again add on to this new modern treatment steps. Microfiltration, reverse osmosis. You can actually take this treat used water to the quality of the drinking water. So UV radiation, but all of these kind of use energy. For example, reverse osmosis energy needs energy to compress, to push the water through the filters. Now, the solution to that again in the next would be replacing digestion, incineration, or landfilling with direct and indirect gasification. Indirect and different gasification. The gasification can be either direct, where you use oxygen, and the product is end product is syngas, which is the carbon monoxide and hydrogen, or indirect, where you instead of oxygen use steam. Indirect direction needs heat. It is a endothermic process, but it makes undiluted gas. Here the gas is in the direct gasification would be diluted by nitrogen. So gasification has been around for a long time, maybe 200 years ago. It's a chemical, high temperature decomposition of organic matter into synthetic biogas, syngas, char and tar, and biofuel. It can convert 1 ton of municipal solid waste to make 2 ton, at least 2 kilowatt hours energy per ton of combustible municipal solid waste, but it can be the indirect can make even up to 5 megawatt hours per ton of combustible sorted municipal solid waste. Here are the, again, because of the timing, here are the reaction equations for combustion of incineration. And the process is exothermic, flame is present, and CO2 emitted. Direct gasification produces syngas, which also is carbon gas, carbon oxygen, carbon dioxide, oxygen, with diluted by nitrogen. It is exothermic process. Indirect gasification is an undiluted syngas. But if you add steam reforming of the carbon monoxide to carbon dioxide, you produce more hydrogen, and the final output of the hydrogen is about the same energies as you put in this process. So indirect gasification followed by low temperature steam reforming of the carbon monoxide into carbon dioxide produces hydrogen, which and hydrogen-rich gas. Other more advanced technologies, heat cooling, production of struvite, ammonium magnesium phosphate, or calcium phosphate. Anamox is you don't have to use aeration. You can use the nitrite to oxidize nitrate and into nitrogen. So, and then we have a lot of new, more efficient and affordable capture of renewable solar energy and solar panels. So, let's go to the 3 lines of integrated resource recovery facility. In line 1, again, it would be a district grade water separation, treatment, and reuse, followed by regional anaerobic treatment producing biogas from high COD liquid used water. Line 2 would be again co-digestion of the high COD semi-liquid sludge and solids. line 3 would be a gasification of combustible, difficult to biodegrade waste solids, wood, carbon, plastic, rubbles, and things, and residuals from sludge from line 2. A power plant would have turbine with a generator. So here is again a schematic. Again, there will be a groundwater treatment. I'm not going to discuss it. That's discussed in other publications. Black water, now more concentrated with COD, let's say around 1,000 to 1,500 milligrams, would require anaerobic treatment, which can be provided in upflow anaerobic sludge blanket reactor and by membranes. Again, post-treatment, the sludge again would go to digester as we had before. Which would be mixed biodegradable. Now, in this case, the solid waste would not go to the landfill. It would go to the gasifier. And gasifier would produce the syngas, so that there will be some gas storage. You can have an engine or turbine. The turbines now are made so they can accept this mixed gas. So the turbines would produce electricity. But there will be also the flue gas, which would contain CO2. So if you need to heat up the gasifier, you would also emit CO2. So there will be some CO2 emissions. So with present advanced technologies, it might be possible to meet net zero carbon goals, let's say by 2035. If we have a water conservation and greywater use in houses and districts, anaerobic treatment using fossil electric energy and emitting CO2 is replaced by anaerobic treatment. Incinerators are replaced by direct gasification. Everything should be like by power plant is a biogas turbine and generator. Increased recycling and circular economy would reduce the production making of the difficult. Excuse me. Increase the recycling and circular economy in production of goods reduces the mass of solid waste into gasifier and landfills. And landfills will be basically only for residuals, but it still would be needed to save a lot of economy. Sequestering of CO2 from flue gases of turbine and combustion engines is difficult because flue gas would be diluted by nitrogen and other gases. So this would need wind and solar panel to generate additional green energy to reach net zero carbons. So fossil fuel from gasifying plastic would be still a problem. Well, this was supposed to be animated, but again, if you want to achieve full decarbonization, you need to think and consider hydrogen. So let's try to design an integrated resource facility that will generate biogas, hydrogen, and syngas. Methane would be generated by UASB reactor, co-digestion of biodegradable municipal solids, methane capture from abandoned landfills, syngas from indirect gasification of combustible municipal solid waste, and it is also intermediate product of in steam methane reforming to hydrogen. Hydrogen from microbial electrolysis cell reactor, from syngas reforming to hydrogen, and electrolysis from water. These are the steps we could use. Now, if you look at the energy content, you can see that the hydrogen is very light gas. It's much lighter it's much lighter than natural gas, methane. Okay, and the carbon dioxide is very heavy, so there may not be mixing between the carbon dioxide and hydrogen. Hydrogen has also very high energy content. Let's say megajoules. Let's do this. Let's call it megajoules per kilogram. 148 hydrogen, 55 methane, natural gas 37, carbon and carbon monoxide 11. Nothing in carbon dioxide. So here, hydrogen is the most efficient energy source and carrier. It is safer than methane because it doesn't explode. Today, gray hydrogen is made from natural gas. It becomes blue hydrogen when the emitted fossil CO2 and flue gas is captured and stored underground and eventually converted to carbonate. So, these are new technologies. Microbial electrolysis cell is a very promising reactor which converts organic biomass directly into hydrogen by adding small electricity to the reactor. 85% hydrogen energy potential recovery from acetates and sugars is possible. But producing hydrogen producing hydrogen from mixed feed is not as efficient. So another advantage of the MEC is that the production of hydrogen is separated from treatment of organic matter and acetates. So it means that CO2 is not emitted, is basically dissolved or converted to bicarbonate, and in this way it's sequestered. So here is the biohydrogen yield potential for biodegradable organic compounds. It's about 12 hydrogens per 12 molecules of hydrogen per 1 molecule of sugar or compounds which have similar composition. X shows a similar composition of CH and O as municipal solid waste and sludge. Hydrogen is produced in the fermentation oxidation phase of anaerobic digestion, but only about 25% of the capacity of the 12 molecules is the potential of the fermentation oxidation. Microbial electrolysis cell converts organics to hydrogen, but it's so far not been top efficient for complex organic waste other than acetates organic. But a combination of low pH fermentation with MEC is very promising and can reach yields which we approach the maximum yield. So this is the situation how it would look. A fermentation switching from digester methane to double step to fermentation reactor combined with the microbial electrolysis cell. I've not been teaching for quite a while, so to speak. So Overall efficiency of hydrogen recovery is much higher than fermentation or MEC alone. I'm sorry for this slide. This slide was again was supposed to show the yield of hydrogen from the various compounds. For example, hydrogen from plastic is about, kind of, if my memory is serving me, is about 0.4 liters of 0.4 kilograms of hydrogen per kilogram of solids. Glycol is a very good source of hydrogen. This indirect gasification is reaching the potential of the hydrogen recovery from the waste. I will probably, those who are interested, who do not have book, I will be sending this slide to you by email. Hydrogen fuel cells are very promising. Hydrogen fuel cells is an energy user dream, an efficient virtually pollution power source, which is buildings can be sited in downtowns, in cities. There are two hydrogen fuel cells can be used: molten carbonate fuels and a solid oxide. Molten carbonate, basically hydrogen fuel cell, is an electrolyte which is between two electrodes, anode and cathode. So there is an anode compartment, you have a cathode compartment, and electrons are transferring from anode to cathode abiotically, in other words, not by microorganisms. So this is a molten carbonate fuel cell. This is the solid oxide fuel cell. Here the electrolyte here is the metallic carbonate, which is solid under normal temperature, but in high temperature at which the cell operates, about 900 degrees Celsius, it becomes molten. Now this is a ceramic oxide, which transfers oxygen oxides from cathode to anode and makes the hydrogen. So the advantage of the hydrogen fuel cell of this molten carbonates, it can take flue gas from other sources and make it a concentrated high carbon dioxide. This is the concentration of the carbon dioxide coming from the cell and partially recycled, and excess going into the flue from as an emitted gas is very high. It's about 70%, and 30% is steam. So if you separate steam from the gas, from this exit gas, which probably should be done very easily by membranes, this would be a concentrated, not 100%, but not far from it, carbon dioxide, which can be then easily sequestrated. The solid oxide fuel cell does not have this capability. Only molten carbonate fuel cell has. Now, electrolyzer is everybody knows that makes hydrogen from water. So again, there is a low temperature and high temperature electrolyzer. So again, it's basically a transfer of the electron, the currents, breaks the water into oxygen and hydrogen. This electrolyzer needs more energy than it produces, but it may be very attractive if you have excess electricity, which is made by green, which is by green energy. So developing of the H2-based decarbonizing integrated resource recovery facility. So regional grade water treatment recovery, municipal solid waste separation into biodegradable, anaerobic treatment of produced biogas to produce biogas, fermentation of biodegradable MS3 with sludge, followed by microbial electrolysis cells to produce hydrogen. You may have other things. You can produce struvite, which is a phosphorus, and nitrogen recovery from supernatant, indirect gasification of organic waste solids to produce syngas, hydrogen fuel cell for electricity and heat production with methane and carbon monoxide reforming into biohydrogen, flue gas CO2 separation and sequestering, producing hydrogen and oxygen by electrolysis to provide endothermic heat to gasification, and heat recovery by heat pumps and heat exchanges. So this is again a three-line system. Now again, gray water treatment in a region or the house, black water treatment as we had before, primary separation of the primary sludge. It's very good because it's a more degradable in the fermentation reactor. Again, USB reactor. But this line produces produces methane. This line produces hydrogen and sludge and municipal solid sludge and municipal solid waste combustible will go to something which I call decarbonizing power plant. And the decarbonizing power plant contains the gasifier, fuel cell, stream methane reforming, and might contain electrolyzer. And what's coming out of that is hydrogen, steam, concentrated CO2, heat, and oxygen. So if you look how it might look, so there are three inputs in this system. Methane. Methane is in steam methane reforming converted to the syngas, which is carbon. It's a hydrogen-rich syngas, carbon monoxide, and hydrogen. It gets sludge and combustible municipal solid waste and gasifies it indirectly into syngas. Syngas storage. Now, syngas can be accepted by molten carbonate fuel cell, and molten along with hydrogen. Along with hydrogen. Now, this gasifier needs heat. Now, heat can be heat to the endothermic heat. Heat can be provided maybe by using some of the hydrogen, some of the syngas. But if you use syngas, that will be diluted with air and it's coming. But might be a situation that we can use electrolyzer. We can use some steam from that, which comes from the fuel cell, and make it into the hydrogen and oxygen. Now, this cell needs water to make more hydrogen because water from the moisture of the municipal soil waste and sludge. And also, if you burn hydrogen with oxygen, you make water. So this would be airless gasifier. The only output would be syngas, and syngas would go back. Now, this FC, molten carbonate, produces heat. Heat can be also used to make electricity. So the efficiency of the system is about could be about 0.6 kilowatt hours per 0.6 kilowatt hours per electricity per 1 kilowatt hour of input, and total maybe with heat 0.9 kilowatt hours per kilowatt hour on input. So this is a very high promising efficiency for the future. Gasifier ash is there is some, but it's only about 5% of the feed solids, and it's methane free. It may not necessarily be landfilled and could be used as a fertilizer or in construction. Again, I have a table here. It's a table here which shows that now the energy yield, energy credit is very high. Energy kilowatt hours, it would be like almost 11 kilowatt hours per kilowatt of the feed, and sequestering of the CO2, or CO2 in combination with the CO2 credit, is about very high, about 8. Kind of unbelievable to most of you. It was unbelievable to me when I was starting to working on me. There is there is not much. There is fossil fuel coming out now. There should be no fossil fuel coming out in 2050 when the power will be also decarbonized. So this system will be a negative CO2 source. I can use it, I can show it, maybe I need 5 minutes to finish. I can show it graphically. So we had the CO2 emissions, positive are down, negative are up. We talked about the system that had anaerobic treatment with landfill gas capture. This black is basically heating of water, which is about very high energy, fossil energy output. Here is the fossil energy input. The second system, here, and here, is incineration. The third system was anaerobic treatment with direct gasification, and the fourth system is again this ANOVA, this system which has a power plant consisting of consisting of indirect gasification and sequestering of the CO2. Now you can see that in the 2000, the biggest problem here in these two systems is water heating, hydrolyzers if you use it, landfill emissions, non-GHG emissions. Again, here again, this is already what I would negative, not negative, but net zero system, which we discussed. The third one is a net zero, and the fourth system is a fully decarbonized system. Again, if you look at the energy, electricity, here the more electricity is used than produced in the first two systems. Here is more energy is used than more energy is made than used, and this is again fully a highly efficient system. The difference between the alternatives 1 and 2 and 3 and 4 are due to switching from the landfill of municipal solid waste limited processing by landfill to co-digestion and incineration and producing electricity by waste heat of incineration. Okay, kind of reading it wrong. So basically, you switch from these two systems, which are landfill capture and incineration, to gasification here and gasification and hydrogen fuel cell in this system. In 2050, the fossil energy and CO2 emission will be zero. So, almost done. Important hydrogen energy components are already being implemented. This is how the hydrogen fuel cell looks like. It was implemented in California, city of Riverside. The startup Solena Group, indirect gasifier, is already commercially available. The description is here again. The plant will produce 40,000 tons of waste each year. Have a capacity to produce up to 3 million kilograms of hydrogen per year. So the technology is available. The advantages of hydrogen is very high energy recovery from hydrogen, methane, and carbon monoxide by hydrogen fuel cells. Hydrogen fuel cells efficiency is much better than combustion near future. The 90% energy recovery can be total energy can be expected, 65% for electricity. Water, steam, and concentrated CO2 are the only emissions from the fuel cell and from the entire system. Hot steam can be converted by hydrolysis to hydrogen and oxygen. High pressure concentrated CO2 flue gas from fuel cell exhaust can be sequestered by carbon capture use and sequestering system, which will be available soon. International can gasify plastic without GH emissions because they will not be produced. Plastics are a relatively good source of hydrogen. Better efficiency can be achieved if a part of the needed heat and DC energy needed for integrated resource facility is provided by solar energy with battery. That is not an option for the traditional processing of used water and municipal solid waste. Here is the list of the concentrating, how you can concentrate the CO2 and sequestering carbon capture, utilization, and storage means means that it will be eventually a system which will take the uh, concentrate CO2 and send it to some kind of geological formation, like, for example, deeps, saline formations and saline aquifers, basalt formations, or conversions CO2 flue gas into soluble bicarbonate and carbonate, and sometimes maybe dry ice manufacturing. So this requires pipeline system, which is already available in some parts, and more pipelines are in planning. There's some other carbon credits. I just switched that. This is basically by landscape, water conservation, uh, reducing irrigation, and here is a future of the, which could be even negative emissions, because uh, this is something which is called vertical forest. So putting a lot of greenery in the cities makes negative emissions. So it means takes the CO2 from the air and converts it to the organic matter. So the possibilities are many, and they're in publications. So I will just read from here. Plastics are very serious problems. That is threatening biota, and when burned emits GHG and toxics. Converting to hydrogen system will significantly increase energy and resources production from renewable sources. Water conservation reduces energy demand. Biogas conversion to hydrogen electricity with carbon sequestering is very efficient. Wind turbines and large inclusion of solar power will become main source of energy. Integrated electricity and heat energy recovery from used water and municipal solid waste can provide significant portion of residential solid demand. Recovery of phosphorus and potentially other sources are possible, and the goal of net zero footprint is probably possible by maybe 2035, and decarbonization by 2050. Here's the list of additional sources on information. I hope that I can somehow maybe send them to you, or you can have them available. And this is the end of my presentation.
Great. Thank you so much, Professor Novotny. We really appreciate it. We will be opening up just for some quick questions. I know we're tight on time, but if anyone has a quick question, you could type it in the chat. And if not, you can email Professor Novotny directly. His email is there in attendee chat. So let's just wait a couple seconds and see if anyone is typing in a question.
Where
What's that?
do I see those questions?
Oh, in attendee chat, the left-hand side of your screen. Click on attendee chat. You see that? I don't see any questions right now. So like I said, You can
Oh,
email Professor Novotny. His email is there. And that wraps up our event for today. Our next event is our annual awards conference on Wednesday, October 21st. We'll be announcing several awards in environmental engineering and science, and this event will feature a keynote speaker, Dr. Andrew Sanderson of Howard University and Chief Medical Officer for the Water Environment Federation. A special presentation by E3S Superior Achievement Award winner Los Angeles County Sanitation Districts will also be included in that event. A link to sign up for that event will be displayed shortly. So I still don't see any questions. So that wraps up our event for today. Thank you so much, Professor Novotny, and thank you everyone for attending. Have a great day.